In today's sharing, what I'd like to share is how to use YML in the RT-Thread repository to implement the CI protection for the BSP. First, let me introduce the CI mechanism of RT-Thread. The CI mechanism of RT-Thread is mainly based on GitHub Actions. It realizes automated building, automated testing, and product generation. Finally, through multiple independent GitHub Actions workflows, developers can efficiently verify whether there are problems with the code, thus ensuring the project quality. The workflow I mainly want to share this time is one of them. This workflow is mainly used for BSP compilation verification. Its core principle lies in customizing the YAML file in the DOT GitHub Workflows directory to achieve the process of BARC, simulating developers manually compiling BSP. Then, let's talk about the process of workflow construction. The current workflow mainly has 4 triggering scenarios, which are triggered when a PR is submitted, when code is pushed, triggered periodically, and triggered manually. The most commonly used one here is the PR trigger. In the following description, the PR trigger is the default. After a developer submits a PR, the CI system will analyze the modified file paths to confirm which BSPs need to be compiled. Subsequently, using the matrix strategy of GitHub Actions, multiple compilation tasks will be created simultaneously. Finally, the workflow will output the compilation results to the developers, helping them quickly locate problems. Next, let's talk about how to analyze the BSP code that needs to be compiled based on the PR. By default, the CI will read the .github all_BSP_compile JSON file to obtain the list of BSPs that need to be compiled. This file also contains the name of the toolchain required for each BSP. The JSON file itself can be passed into the action as a matrix variable. After the CI reads it, it will create corresponding compilation tasks according to the BSPs defined in it. However, as the number of BSPs increases, the execution time of the CI will become longer and longer. The time consumed during full-scale compilation is shown in the following picture. Especially when a PR only involves local modifications to a specific BSP, full-scale compilation at this time will obviously lead to low efficiency. To solve this problem, we can analyze the differences between the PR submission branch and the main branch to figure out which BSP files have been modified and thus know which BSPs need to be compiled. After extracting the file paths of the BSPs, we match and filter the paths with the BSP information in the JSON file, and finally generate a list that only contains the BSPs that need to be recompiled. This list will be passed as a matrix parameter to the subsequent build workflow so as to achieve compilation according to requirements. Based on the introduction of the git diff function, we can further implement the file status display function. This function will organize the file changes in the PR into a clear status report, so as to evaluate the scale of the modifications in this PR. Next, take a single task in the matrix as an example to illustrate its process. When the matrix is passed into the BSP building task, GitHub Actions will create independent building tasks for each BSP defined in the matrix. The core processes executed by these tasks are the same, but there are specific differences among different BSPs, such as the toolchains used. The first step of the building process is to download the required toolchain. Here, the GitHub Actions cache mechanism is utilized. The workflow will cache the downloaded files, and when needed later, it will directly obtain them from the cache to avoid repeated downloads. Each independent task created by the matrix contains the BSP path that it needs to compile. This path, together with other necessary information, is passed as a parameter to the compilation script tools CI_BSP_buildings.py. In the compilation script, the core function is to execute the compilation of the BSP according to the passed in BSP path. The process mainly includes simulate the initial configuration, generate the initial rtconfig.h configuration file by calling menu config, execute the compilation. Subsequently, call the sconce command for the actual building. After the compilation is successfully completed, the workflow will output a success status indicator and relevant information in the summary section. If an error occurs during the compilation process, the workflow will prompt the error location. Developers can quickly locate the problem based on these prompts, enter the corresponding task log to view detailed error information, and thus efficiently debug and fix it. By default, the BSP compilation is only based on the preset default configuration. However, in order to verify whether a specific functional configuration can be successfully compiled, a more flexible method is needed. Therefore, the attachconfig functional module is introduced. Its working mechanism is as follows. Automatically parse the YAML configuration files in .ci attachconfig under the BSP directory. Intelligently identify the functional modules that need to be enabled. Create exclusive compilation tasks for each independent configuration. In continuous integration, the files generated after the build is completed are usually called build artifacts, or simply artifacts. These are the packaged data files output from the build process. In our BSP CI process, we can upload the generated build artifacts after the compilation is successfully completed. These artifacts usually include the compiled binary files. The main advantage of this is that when you need to quickly verify the compilation result of a certain BSP, you don't need to rebuild a complete compilation environment. You can directly download the corresponding build artifacts from the CI, burn them into the target hardware, and then run and test them, which greatly improves the verification efficiency. Next, I'd like to share how to incorporate a new board support package into the automated compilation and testing process. The all_bsp_compile.json file located in the .github directory of the project. This file defines the CI build matrix, that is, the list of all BSPs that need to participate in the automatic compilation and testing. Adding steps, simply add the path of the new BSP to the corresponding category list according to the existing JSON format in the file. Points to notes when adding correct categorization. Each BSP must be added to the correct category. For example, if the new BSP you added is for the STM3 to F7 series, its path should be added under RTT_BSP or other corresponding category names. Create a new category. If none of the existing categories are suitable for your new BSP, you can create a new category referring to the format in the file. Trigger CII. After completing the modification, submit a pull request containing this change. After submission, GitHub Actions will automatically trigger the CI process to compile and test the newly added BSP. View results. To view the CI compilation details and results, Step 1. Scroll to the bottom of the PR page. Step 2. Locate and click the option with a magnifying glass icon. Step 3. In the pop-up interface, you can view the complete execution process of the CI workflow and the compilation results of each task. The above is the core content of my sharing today about the BSP CI workflow, covering the task process, build, artifact handling, and how to add a new BSP. Thank you all for listening.